So I'm I just had
So bad.
Oh,
Except I have bad news.
yeah.
Is SP1 like from
Okay, so next talk in the morning session, we will have our amazing practitioner Ron Rothblum, who will tell us about his new work that I can't even pronounce.
So great to be here, back at the Simons Institute. What I want to tell you today is about actually an implemented proof system called SP1. I should give maybe a little bit of context is that, I've been working in this field of proof systems for quite a long time now, I'd say 15 or so years.
Or you're working in a place called
I both. I'll try not to be too succinct. So I've been working on the very theory side of proof systems for a long time, and somehow by accident, my theoretical research became sort of interesting also in practice. And I had a sabbatical coming up, so I decided to, the accident. I think it's just I don't know, let's not get into it, take it offline. But anyway, I had a sabbatical coming up. I decided that I'd like to learn what actually happens in practice. I've been working at Succinct for almost a year now, trying to learn and trying to develop some new stuff. So I want to tell you about that today. One thing that you should take into account is that in contrast to what Yael said, I'm not really a practitioner, I'm a pretend one. So I probably won't know how to answer a lot of practical questions, but hopefully I can tell you a little bit about what we've been doing. Cool, so and I'll also explain what these things mean. So what is this talk about? So this talk is about a state-of-the-art proof system called SP1. And specifically, it's about a new version, which is called Hypercube, which we've announced sort of, but hasn't officially been released. So it's really kind of happening now. It's implemented and so on. And it's a complex system. I won't be able to describe everything, but I'll try to describe what I think are the interesting parts. In particular, one aspect which is really novel to our proof system, I'll try to cover in more detail. And something I definitely won't be able to cover is that there are other approaches to what we'll be describing. I won't be able to cover all of these. So in general, the talk is going to have sort of three parts. One is, what is this proof system? What is it trying to achieve? And kind of the broader context. The second part will be, how it works, broadly speaking, but in a way that most other similar proof systems work. And then the last part of the talk will be about this kind of novel component that we've introduced. So let's start with, what is SP1? What is this proof system? So it's what people call a zkVM, or a zero-knowledge virtual machine, which is a term that I, a year ago did not know what that means, so let me explain to you. It's a succinct argument for a RAM computation. Okay, so I'm trying to translate to the theoreticians what this means. So succinct argument for a computation expressed by a RAM computation. You have, RAM operations. You can read, you can write, you can do addition, multiplication, and so on. Now, so the goal is to prove the correct execution of a program written in this sort of RAM machine language. And you might be wondering, what is this zk part? And I'm also still wondering. So the privacy or zero-knowledge aspect is really optional. So you don't have to have it. In case you do have it, it's called a zkVM. So yeah, these are real terms. So just so you're aware. Okay. Yes.
Succinctness gives you some zk for free.
Sure, but
They call it zk.
yes, this is what practitioners call the zkVM.
That's the honest.
I guess just practitioners, a lot of times they refer to ZK and they mean snark.
Yes, so when they say zk, they mean proof systems.
Yeah.
That's the terminology. So just so we're on the same page. Okay, so there is nowadays massive interest in these sort of zkVMs, mainly coming from the blockchain industry. And just to put this sort of a little bit in perspective, this is a quote just from last week. So I think most of you should be familiar with Ethereum. It's the second largest blockchain. I think it has a market cap that's kind of like...
This is the ZK that's not ZK.
This is ZK, that's not ZK. Yes, absolutely. So what they care about is succinctness. Like for this thing that I have here, they care about succinctness only.
I mean, there are some applications.
There are, but the reason,
ZK.
the key interest in this domain is about succinctness.
Do they care about zero knowledge?
So a little bit, but mainly succinctness. Yeah. So Ethereum is one of the large blockchains. The market cap is something like a medium, small, the GDP of a medium to small size country. So it's very, very big. And this is a quote from last week. So Ethereum is going all in on zk. So it's not like some side thing that they think they could improve stuff a little bit. There is massive interest, and that's sort of like I think really exciting. And to kind of show this a little bit more, here's another like slide that I stole. So this is a list of all zkVMs currently being developed specifically for the goal of proving stuff over Ethereum. So it's a list of like I think more than 30 different projects being implemented. So there's massive interest. Maybe I can point out some of these are by sort of people from this kind of community. So there's Jolt over there, which is developed by Justin Taylor, who's going to be talking about related work on Friday. Ligatron is a work by Mutu or is a company by Mutu and Kermit based on the Ligero protocol, which is developed together also with Yuval. Cairo is, of course, the Starkware thing, developed by Eli and based on work also with Ale and others. So there's a lot of excitement and a lot of action and a lot of money being poured into developing these. Do we actually need 30? I don't think so, but yeah, that's going on. And this is coming from a website called ETH Proof, so ETH for Ethereum Proofs, which also does run some benchmarks. So you can go to this ethproofs.org and see like these proof systems being run in action in production, the time that it takes to prove Ethereum blocks, and so on, and the cost. So that's the landscape in general of what is a zkVM. I want to tell you about the particular one that we are developing at Succinct. It's called SP1, Succinct Prover 1. So it's the fastest, best zkVM, but any other zkVM will tell you the same, but I'm being honest. So it's developed specifically, we talked about RAM programs, and now we need to say, what kind of RAM program. So it's specifically for the RISC-V instruction set, which is an instruction set also developed from the academic community, but is very popular also in practice, not for reasons of... Berkeley. It was not developed for reasons of... By Shafi? Okay. But not developed for the purposes of zk, but otherwise. It includes the things you would expect, so things like integer arithmetic, so you can add, you can multiply, you can do, shifts, XORs. More interesting things are the way, like memory, you can read stuff from memory, write stuff from memory, you have conditionals, ifs, and so on. So the things you would expect from a RAM program to have. And now the general idea with SP1 and also with competing systems is that you write your code in a high-level programming language. So people tell me that a popular one nowadays is Rust, but think of something like C++ maybe. You use a compiler to compile it down to this sort of like assembly language, RISC-V, and then you run the proof system, you generate a proof, and you verify, the things that we write in introductions are happening. One thing I should mention, we actually are, and others are as well, we're actually extending the RISC-V instruction set. The reason is that one of the most popular things you want to do, especially in a blockchain context, is do hashing. And if you were just to write down the hashing in this instruction set, it would be very expensive. So what instead you do is sort of, the way I think of it, you extend the instruction set to support, in addition to addition and multiplication, also like compute SHA. So it's another instruction which you sort of add on. So now let's this is sort of our approach to it. A different approach, which was taken, for example, by Elliot at Starkware, is that they developed their own instruction set called Cairo, and they developed it in a way that is designed to be friendly towards arithmetization. And so there are two competing approaches. Do you use an off-the-shelf instruction set, or you develop your own? In terms of pros and cons, I think the pros of using this existing instruction set are, there are multiple pros. So I think, first of all, your programmers, your users don't need to learn the new instruction set, a new programming language. And mainly, there's a lot of tooling apparently involved in programming. So you can use all of the existing tooling that already exists. And even more than that, usually your programs are using a lot of existing libraries. And these libraries are probably haven't been developed in your made-up new instruction set, but rather in an existing one. So you can just use them off the shelf, which is pretty amazing. The con, of course, is that RISC-V, despite being developed at Berkeley, I think they didn't have succinct arguments in mind. So it wasn't specifically designed to be arithmetization friendly. So it makes our work as proof system developers harder. OK? Cool. So that's SP1. I want to talk to you about this new version called Hypercube.
Just one, what's the ballpark overhead of compiling from one to another? I mean,
So it's large enough that they don't do it, to the best of my knowledge, at Starkware. So you would think, I would think off the top of my head, they take Rust, just compile it to their thing, and everyone's happy. You get the best of both worlds. They have not done it yet. So I guess it is too much to be good in practice. But I think that it is maybe something they're thinking. I think they're actually thinking of like developing stuff for RISC-V as to have both, cover both bases. So I want to tell you about the new version of our proof system. It's called Hypercube. So maybe before I introduce it, I should say that the previous version was all based on sort of Stark technology. So mainly when I say Stark technology, I mainly like kind of almost exclusively using univariate polynomials. And for those who know it, things like the Phi protocol and so on. But I joined the team, and I really like multivariate polynomials. So I convinced everyone to switch to multivariate polynomials, specifically to multilinear polynomials, and rely on tools such as SumCheck and GKR. Okay? So we are taking what people call a multilinear-based approach, which is much more traditional in the sense if you go back to early papers and PCPs, that's sort of the approach that they were taking. You have to do things you can't use them off the shelf. So we'll talk about that. Just to prove to you that I know a little bit of the concrete stuff, so we're using fields, and the specific field we're using is the 31-bit prime field, which is specifically this one. It's for some reason it's called the baby bear field. I have no idea why. Maybe the main interesting thing about it is that if you look at this prime and you consider the multiplicative subgroup, it has order p minus 1. So you have a big power of 2, and that's very useful for doing things like FFT and Phi, which relies on FFT. So that's the main consideration for this choice, even though nowadays we do know that there are better choices. We just haven't switched to them because of some other considerations. Okay, so this is the field in which we encode the data. If you go and you run SumCheck with this kind of field, you're going to get very poor soundness, right? Because the soundness is kind of proportional to the inverse of the field size. So the data is encoding this size field, but when actually running things, you use an extension field. So it would be a degree 4 extension field. So you get around 120-bit field when actually running protocols.
When you say better fields, you mean other fields of low Hamming weight, but odd, or?
No, so the main consideration is the complexity of hash functions over this field. And specifically, we'll get to it, we're using the Poseidon hash function. And for the Poseidon hash function, the inner permutation here, I think, needs to be degree 7. And with a different choice of field, you can get it down to 3, and it reduces the complexity. So it's specifically the koala bear field. That wasn't.
So it's important to use these external hash functions rather than a polynomial-based hash function, say, or something?
What do you mean by polynomial-based hash
I mean,
function?
you could do an algebraic hash function.
So these are people have developed algebraic hash functions specifically to be friendly towards, so that it's cheaper to prove them.
And those are the hash functions you use here?
Yes. And this discussion was about what is the degree of the hash function, and we use this field, it needs to be a little bigger. And one thing I should say, and we'll get back to this more, we are really optimizing for proving on a GPU, because it turns out the GPUs are just much faster, believe it or not, than CPUs. But it's a very different architecture, so we have different considerations, which I think also lead to really interesting theory questions. We can talk more about that after.
So, what do we know about these hash functions and their security?
So first of all, they were proposed by serious people from the cryptanalytic community. And I don't know anything about security of other hash functions. So we know the same. From my end, I know the same as about SHA and about this. There are newer hash functions. They follow things like a sponge-like construction, which is people are like and think is secure. And you can prove that if the underlying permutation is a random oracle, then it works nicely.
You are confident enough to deploy this in the world?
No. but other people are.
But it's part of your
Many things
SP1
fail in
thing.
the real
Yes,
world.
but it's also part of many, many other things. I should say, actually, because I'm involved with it, the Ethereum Foundation is running, really wants to understand better the security of this hash function. In particular, it's running a bounty program on trying to study this and show attacks. As a matter of fact, I have a recent work with the collaborators from the Ethereum Foundation about an attack on Fiat Shamir. I think Gal is going to talk about something related later this week. And that attack came from, they said, here's a hash function, a new hash function, try to attack it. And one of the things they said, give an example of, break Fiat Shamir security for a protocol of your choice. So I told them, that Shafi and Yael have an attack. And from there, this led to the eventual attack on
Maybe one interesting point about Poseidon is that, inversion, which is normally an expensive operation, and it's a nonlinear operation that is useful for hash functions, is easy in the context of proof systems, right? So this is kind of the field inversion, right? That's an ingredient which is easy in the context of proofs and is.
So from my perspective, I think one thing is that you can choose which field to use it over. So in particular, we're going to use it over our field. So that's already the operations are native. So it's an arithmetic function over this field, and it's low degree. So from my understanding, these are the main things.
Low degree to prove, not to compute. I think.
So you cannot be low degree to compute, but it's sort of the round function is low degree, and then you compose it. But when you prove, you do Okay. So people here usually are interested in soundness. I'm also interested in soundness. This entire
But if you're not interested in zero knowledge, you've got to be interested in something.
Yes, or in completeness. Completeness is also is also a thing. The engineers really care about completeness, So with soundness, we're relying on a lot of assumptions, some of which are kind of shaky. So first of all, just to annoy Yuval, I'll say that the system is targeting 100 bits of security. The reason it annoys Yuval because it's not clear what this means. I also don't know what it means. That's why it's in double quotes. I'll tell you what it means from my end. It means that if it doesn't have 101 bits of security, meaning that, and what this means I do know. It means that if you're allowed to compute the underlying hash function 2 to the 101 times, you'll break this totally. Okay? What does it mean to have 100 bits of security? I know what people mean it means, but it's very unclear, so I don't want to say.
It doesn't break totally.
But what does break mean? So people, when you're concrete numbers, what's the probability? What are you allowed to do? So it's kind of I think people usually don't mean it in a well-defined sense.
But they mean it as a lower bound, not as a
lower bound. So exactly. So as a lower bound, they mean as well. This is with this you can break it.
It doesn't mean what they think it means.
Sure. Yeah.
There are other systems that can also be broken in time to the 101. That would be more efficient than SP1.
Yes, absolutely. Yes, for sure. Yes. I agree. I agree, and I don't have more to add. You might want to use Dan's suggested system that also does not have 101 bits of security.
And they're very efficient.
Yes, which is more efficient. Anyhow, in terms of our soundness and to try to achieve soundness, we are relying on a bunch of assumptions. So for one, we're using this Poseidon 2 hash function. And in some places, we are treating it as a random oracle, in particular to achieve Fiat Shamir. Also another thing called the multi-set hash. I don't want to get into that. But the main thing is Fiat Shamir. And going back to Benedict's talk yesterday, we and this entire community are using, in terms of the analysis, say Fiat Shamir, we're treating it as a random oracle, but in terms of recursive proof composition, we do need to know the details of the implementation. Is that great? It is not great, and I think this community really should study this more. We don't know attacks. Okay. Another thing, going back to what Benedict said yesterday, so we're going to talk about it more, but we use recursive proof composition. We know that when you analyze it in the real world, not in idealized models, there is a loss in security in what the proofs give us, but we don't know attacks. So we're relying on there not being stronger attacks. Again, very important question to study. We're relying also on discrete log over elliptic curve groups from all our problems in life. I think this is the mildest, so let's skip that. And it's also easiest to get rid of, and I think at some point we'll want post-quantum security, and we'll probably get rid of it. And lastly, this is somewhat related to Hadassah's talk. So we're relying on a protocol called FRI, or a variant of FRI, for which this is an information theoretic protocol. It's an IOP or IOPP even, for which people have, including Yuval and others, have proved that it is sound up to an extent. But we and others in this community are conjecturing that it is even more sound than what we can actually prove, that it is sound up to the place where it is clearly not sound.
Like 100 bits.
Yes. Yeah. But at least interestingly, this one is sort of an information theoretic conjecture, which you could hope to prove, or disprove. It's not like cryptographic in nature. Yeah.
I don't understand what does it mean that soundness relies on no security loss from recursion. What do you mean?
So were you at Benedict's talk yesterday?
Yeah.
So when you do recursive composition and you try to do the extraction argument, as you go from layer to layer, the running time of your extractor doubles, sort of from layer to layer. Which means that if you do this for a lot of layers, you're doubling a lot of times. That's very expensive, and you're getting a slower extractor, and you have a stronger assumption. That's what you can prove. On the other hand, we don't know an attack that matches this. And the assumption here is that there is no attack that matches this. You don't lose this thing that sorry? Yeah.
And so you can do recursion as much as you like and you lose nothing.
Yes.
That's an assumption.
Yes. Yes. And there is no attack that shows us differently. And I think it's really interesting even to show, I think Benedict said this as well, to show a contrived even example of which there is a loss. Okay. So one thing that we've been really pushing for as a community, and especially at Succinct, is something that is called real-time proving. And the idea here, which is really encouraged by Ethereum, is that it turns out that computing the next Ethereum block in the blockchain is something that takes around 12 seconds, I guess. And what they're really interested in is, are you able to kind of tag along? So as you are computing the next blocks in the blockchain, generate proofs at the same time. If you're able to do that, then you can just prove the correctness of your blockchain as it develops. So there's a big push of being able to prove the correctness of an Ethereum block in the time that it takes to generate the next one, which namely is 12 seconds. So we were really geared towards that. And as a matter of fact, with this new release, we were able to achieve something which more or less gets it. We can say in a second more about that. So with this new system, it takes 10.3, which is less than 12, so we're happy. It's an average block. It's not every block, but it's pretty good. Yeah. So to this extent, to achieve this, we're using something like 160 GPUs, which I don't have at home. Probably you don't either. So it's expensive, and I mean, it's estimated to cost this much money. I say estimated not because we stole them, but we rented them. But apparently, if you want to buy these GPUs, you can. It's not. It's a lot of money for me, but for a blockchain, it's not that much money.
You know what the operating cost is to prove a block?
Like a wattage and so on?
Yeah, I mean like in dollars ideally.
I don't.
This is the cost per year? Or
this is the cost for setting it up. And Benedict was asking how much electricity it is, or the equivalent thing, and I don't know.
Do you know what are the operations being proven? Roughly, how many hashes? In the order of thousands? You're verifying signatures as well, imagine?
I'm not confident enough to say now, so let's maybe take it offline.
Thanks.
Yeah.
How is 12 seconds in practice?
What do you mean? Actually, I'll show you. I'll show you in a second. Or in 12 seconds.
Fifths of a minute.
Okay, so first of all, here's a graph from the marketing team. I don't know how to do these fancy things, but this is showing the time that it takes for an average block. Average, I mean in the empirical sense. So we ran this on a very long, 10,000 blocks of Ethereum, and we computed the empirical average. So you see the median is somewhere around 10-ish, and we're covering something like around 94% in the desired 12 seconds or less. Okay? Any questions, by the way?
You haven't talked about energy.
Yeah, because I don't know. But I'll touch upon it soon.
Do you know how much it costs to rent the GPU for this time?
I think I know, but I'm not sure I'm supposed to say, so it's expensive, but expensive for a person, not for a company. Yeah.
So when you say for a person, not for a company, I mean, let's say Ethereum blockchain, the block is like the result of many people doing many things. Do you know anything about can this proving process be
distributed
or
So it's already distributed because we're using these 160 GPUs. You could maybe potentially distribute it
you
among.
said 160 different GPUs.
Yes.
I missed that.
Yes.
Okay.
So it's very distributed.
Okay.
Is there a reason that you're using the NVIDIA line that's targeted at gamers instead of like the AI line?
I don't know.
Okay.
I think maybe cost performance is good.
Okay, I just figured I would have more sort of relevant.
No, I should actually say, I should correct myself. So I think the AI guys, they're using, I don't really know this stuff, but I'll try. They're using stuff called tensor cores inside GPUs. So that's sort of what the part of GPUs that's optimized for AI. We're not using these, so it sort of makes sense. I don't know if that answers it, and I'm not sure about what I'm talking about. Yeah.
Just to calibrate, like how big are the statements?
Someone asked me as well. Big. Yeah. So in what quantity?
Like if you want.
How many RISC-V instructions?
So I don't know the answer to that. But yeah, so I'm not on top of that, or like not like if I sit down and I reconstruct, I'll be able to, but I don't want to answer on that.
So are these just proving the transactions on the chain, or also proving the consensus of the community?
I don't know.
So is average block like the metric you want to look at, or like is there?
No, so I'll touch upon that in a second. Yeah.
Is this like if I added like 2x number of GPUs, would this go half the time, or like what?
Not half, but it would improve not by a ton. Okay. So we are actually, no, it won't improve at all. So actually, we have, you see here, it says 200 GPUs, but in reality, we're only using 160. But we rented 200. Yeah. So we've saturated the parallel.
Serial bottleneck.
Yeah.
Just to make sure it's like your argument might involve history.
Yes. Okay, so actually, you know how, for the parents in the crowd, you know when you teach a baby to walk, you go like this, they grab your hands, and then you go back. So similarly with the Ethereum Foundation, so they said 12 seconds, but now they've changed it. So they're moving the goalposts. So they have a new target, it's from last week. So they're not happy anymore with 12 seconds. So first of all, they say they want 128 bits of security. So neither mine nor Dan's systems are good enough anymore. But actually, they also said that maybe 100 would be okay in the beginning. They're insisting on a trusted setup, meaning that it has to be a uniformly, the common random string has to be uniformly random. Means you cannot use, even internally, something like Groth16, which has a structured random string.
Transparent setup? Transparent?
Yeah. Sorry? Do they insist on uniform, like transparent, like, I'm not sure what the fine print was.
Transparent. No, but when you say uniform.
Yeah.
I mean, everyone is trusted.
Sorry?
People disagree with the first word on the slide.
About trusted or?
Yeah, the one.
For me, the trusted setup is the uniform string. Sorry. But maybe the terminology that people use is transparent. Whatever. Yeah. They also, going back to a question that was raised before, they want to be able to prove 99% of the Ethereum blocks, so not just average and not 94 that we achieved, and also under 10 seconds. And the idea is that, for the remaining, 1% of outliers, it's probably more about issues of like changing the Ethereum protocol to disallow them. So they're okay with 99%. They also want to reduce to 30 GPUs. Remember that baby? So we have our work cut out for us, but I think it's manageable. They're also insisting on the proof size, which is something we weren't really optimizing for. So our proof sizes are in the megabyte, like 1 megabyte, and they're insisting on 300 kilobytes. I think it's doable, in particular via techniques were designed by people here. Maybe I'll talk about it later. Question?
The reason for the lower GPU requirement is part of their trend that they used to.
I think they didn't believe we'd be able to. I think they didn't believe we'd be able to achieve what was achieved, and now they're getting greedy. Because I don't think it's. But I don't really know. I don't think it's a crazy cost. They do want, not just like one prover to run. They want like many provers to run. They want to make proving relatively cheap. So level like a very enthusiastic hobbyist could do it.
What is the cause of variability in the time for proving?
The actual instructions that you do. So it depends. So if you think of it.
Okay.
Yeah. So there are different costs to different operations. Yeah.
Ron, how is Stark doing with this?
I don't know. I don't know if other people do. I think one.
Alessandro, can you comment?
You know?
I don't have numbers off the top of my head.
I think Stark, I think Starkware has a new release called Stew, which is very performant, but it's like it's for CPUs, And GPUs automatically give you a really nice improvement. And in particular, our CPU implementation is not optimized, so it's kind of like not apples to apples.
What are you actually proving? The signatures are valid and consistent?
So I don't know the details of the Ethereum blockchain, but it's developing. So the new block is valid and correct. Yeah.
I mean, it's the same thing that a new user downloading the blockchain would do.
So to verify the history.
To verify the
Yeah. Okay. So I want to show you how this thing works. Now we're getting, I think I'm late, very late. But the second part of the talk of how, in general, these zkVMs work, and in particular our system. And the basic idea is an IVC, the way that Benedict was describing it yesterday. So you break down the computation into sequential blocks, and you start sort of computing. You start executing these individual blocks. And as you finish executing block I, you can immediately start generating the proof for it. Each block you can prove on a separate GPU. It's independent of the other guys.
You're using blocks now in a different way than you did before?
I was using blocks before? Yes, it's a different way.
Okay.
Yeah,
You mean block of computation?
Yeah, now you can forget about all the blockchain things.
Right.
Forget.
So computation now.
Computation is broken down into.
Let's say verifying a digital signature. That computation, I'm
Yes,
breaking it
yes.
into small pieces,
Yes.
which you call blocks.
Yes.
Okay.
Yeah.
Blocks.
Sorry?
Blocks.
ZK.
Okay. Block. Actually, people call it shards, but I didn't want to confuse you with the terminology. Never mind. Ryan, you have a question? No.
So these blocks have nothing to do with.
No, nothing.
Let's talk about it. Let's talk about it.
So these blocks have nothing to do with the blockchain block.
No. Independent. I'm also running out of time, so like think twice if you have a question. If it's important, then ask.
It's going to be a block tree.
I think it would be a very different understanding of what you meant by block if we thought it was blocked.
Right. No, that's a great question. Yeah. And then the proofs are, I'm not saying any questions are bad, but but anyway, I'll do whatever we manage. So then you generate the proofs and you prove them via recursive composition. Why do we do this IVC? First of all, it allows you a massive parallelization, right? As you're computing, you finish this type of block, you ship it off to the GPU, you start proving immediately. And you can do this all in parallel. A major other thing is memory. If you try to do like one proof system, just proving all of this, in many but not all proof system, the memory scales with the complexity of the computation, which you would like not be able to do here. And let me skip the third point. Never mind. Okay, so how does an IVC style proving look like? So Benedict already described it yesterday. I want to go over it quickly now. So you run your computation. This is sort of the axis as time develops and you're computing. And then as you're computing, you immediately start proving. Okay, so the green block is a proof for the first part of the computation, first block of the computation. You generate the second block, generate the third block. Already in parallel, you can start merging them via proof composition. So you can do all of this in parallel. Okay, so this is the extent of my PowerPoint abilities. Let me show you what the fancy animators at Succinct can do. So let me describe what's going on here. So you're seeing that so this is proving an Ethereum block in real time. And what you're seeing here, let me see if it restarts. You see the green stuff is just executing the computation. And as you're executing it, you start proving. So things that appear in pink are beginning of like proving. And once it turns purple, it means you've finished proving. And then the light blue is the merging. And you kind of like, in terms of parallel time, which is what we really care about, it's like this path. From n to 10, it's like 10 seconds. Okay, and like the height corresponds to the parallelism. Okay. So now so we understand we're using Valiant, we're using IVC, we're happy. The question is how to prove individual blocks. And if you asked me this a year ago, I would say, who cares? The constant size, around whatever proof system, everyone is happy. So it turns out that in practice we care a lot, and the major that is sort of the interesting and the exciting part of the proof system, is how to prove individual blocks. So from here on, we can forget about the IVC picture and just think we want to develop a fast monolithic proof system that doesn't use IVC, because we're proving the individual blocks. Cool, so I want to tell you about how we do it. As I said before, the proof is based on multilinear techniques. So to do that, I need to introduce what are multilinear polynomials and the multilinear extension. So I think this is maybe the only slide I could steal from different talks. So what is a multilinear extension? So suppose you're given a function f. It's defined on 0, 1 to the m. Okay, and it outputs field elements over our favorite field. Standard sort of claim is that there exists a unique a multilinear polynomial, which I'll denote always by f hat, which now takes as input field elements, instead outputs field element, with the property that it's an extension, so it agrees with f on 0, 1 values, and it's multilinear. Okay, this is kind of standard. Moreover, you can express this f hat as a linear combination of the truth table of f, where the coefficients are these very nice EQ values, which maybe I'll skip over what they are. One important thing that I'm going to use quite a lot in the talk is if you have two multilinear polynomials, f and g, and you're able to show that they agree on 0, 1 to the m, I claim that this implies that they agree everywhere. You see why? It has to do with the uniqueness, right? So if they disagreed, this will not be unique anymore. And we're going to use this. Questions? Cool. So we want to develop a fast proof system. Let's see how I, as a theoretician, would have thought this can be done a year ago. So first, you execute the computation. We've zoomed down to like one block. You execute it, right, and you write down the entire trace. So all of the steps that you did in the computation and the entire memory contents as you went along. You take it, and you view it as a truth table of a function. So I'll write it as capital X from 0, 1 to the m to f. And we encode it. Okay? How do you encode it? You kind of encode it as a multilinear polynomial. You take x hat, which is the multilinear extension of the entire trace data.
By trace, you mean the tableau of the computation?
The tableau, everything, yeah. So you take this, you compute x hat, you commit to it cryptographically, and now you express the correctness. You want to check that this is a valid trace, a valid tableau. You want to express it, and the way you do it is by writing down a low-degree constraint polynomial, and you write it down in such a way, and this dates back to BFLS from the early 90s. You write it in such a way as a composition of this constraint polynomial, somehow composed with actual data. Okay? You write it down, and you write it down in such a way that for this composed polynomial, it is a correct execution if and only if the composed polynomial is identically 0 and 0, 1 to the m. If you manage to do this, again, this is standard BFLS. You can now use a sum check or a wrapper around sum check called the zero check protocol to check that this is indeed the case. People are familiar with this, I hope. Cool. So why are we not done? Why were we not done in the 90s already? Okay, just a summary. And this is really following, the Killian style approach. You cryptographically commit to the computation trace. You run the sum check, zero check protocol to check for consistency, and you decommit to the relevant parts. So when you run the zero check, it will query some points in the encoding, and you open them up. Oh, and you do fiat shamir also, and hope for the best. Right, so that's that kind of the bird's eye view, what I would have expected things to look like, and to an extent, it is what they look like. But what are the problems? So problem number one is how do you commit to the trace encoding x hat? And going back from my early years, this is what I would have expected maybe. Write down x hat on all of f to the m. Just write it down, do a Merkle tree, and now when you want to open stuff up, run a low-degree test and local correction of polynomials, and check, and everyone's happy. The problem with that is sort of the encoding time is huge, right? You need to write all of f to the m. So if using multilinears, it's super polynomial. If you scale it up, it will still be a large polynomial. You cannot do that. Okay, so you cannot take this approach. So what happens? Right. So what we would want is to be able to commit to this entire multilinear polynomial in time that is linear in its size, 2 to the m, and also generate evaluation proofs at the same time. And to do that, we use sort of what Das was talking about, and I think maybe Benedict was mentioning, or maybe Pratyush was mentioning also yesterday, a polynomial commitment scheme, or PCS. So we want to succinct commitment to a very large polynomial, a multilinear polynomial, so that later we can prove evaluation proofs, p of x is equal to y, and so on. And you have different variants of this. You can think of this problem for univariate polynomials or multivariate. You can think of different fields, and we have different solutions for these different things. The basic approaches, like two classes of approaches that people are considering in practice. One is via proofs of proximity, like IOPPs, which Das was talking about extensively in the session before. And in particular, in SP1, we're using Hadass and Benny and Ben's system called Base4. There are other approaches, which I think Pratyush was touching about more, based on discrete log or lattices or pairing, which I'm not going to discuss whatsoever in this talk. Okay, but again, the goal is to commit to the entire computation trace in a succinct way. So far, we're happy?
What's M? How much is M?
In practice?
Yes.
So we're talking about these individual blocks, around 30.
30?
Yeah.
So which one do you take? Which of the approaches do you guys take?
So we take the proof of proximity. So it's an IOP. It's very much PCP machinery. And so you want a proof of proximity that's something, yeah.
But with a multilinear approach.
With multilinear, yeah. Yeah. So both like the claim you want to do is multilinear, but so really the claim you care about is multilinear. The approach that you do in this thing inside internally uses a lot of univariate polynomials.
I got it.
And in particular relies on a lot of like some things like the Phi protocol and so on. But I'm not going to go into that. Second problem is that the size of the trace is quite large, right? So if it's a t-step computation with space s, it's t times s to write down this entire thing, which is a lot in practice. It's much longer than just the execution time. And sometimes in theory we say, this is small, don't worry about it. We worry about it. So you don't like that. And the way this is solved is via techniques from the memory checking literature, in particular works by Moni and others from a while ago. Also in Berkeley? No. Yes, also in Berkeley.
It was done in Café Depresso.
Okay.
Does it exist?
Newton.
So the idea would be you write down the computation trace. So you write down all of the instructions that were run. So for example, add I stands for add immediate. So you're adding the value 2 to 3. The claimed result is 5. And you write that down into memory address 3241, whatever. So you write down the list of instructions. With you write it down, like what happened, sort of. I did this, and so on. But you want to check that, when you read something from memory, what you read there is the last thing that was written. There's a mechanism based on Moni's work for doing this. It's the way it is used inside proof system is something that's called a memory argument, which relies on top of it on something called a lookup argument. I won't have time to discuss it. I'll just say that the one we use in SP1 is something that's called logup GKR, which is based on the GKR protocol proposed by Habuk and Papini a couple of years ago. Okay? So let's not worry about memory consistency for the rest of the talk.
Does the memory checker itself use hashing inside? So these are instructions that have to do with hashing? Or
no, so it's using a very vanilla thing from the paper. And
it's offline?
It's offline.
Okay.
Yeah. It does internally use there is an IOP mechanism which involves hashing, but not from yeah. Third problem, if we talk about we need to check the constraint polynomial everywhere, right? What does the constraint polynomial look like? Well, it needs to, depends, right? If it's an addition instruction, it needs to check addition. If it's a multiplication instruction, it needs to check multiplication. And the CPU does a lot of interesting things. You have to do all of these. And the annoying thing is that when you eventually do the zero check or sum check, you're paying a lot. You're paying the complexity of the constraint polynomial everywhere, right? So really, you're paying the complexity of the entire CPU on each and every instruction. And you think of it, I have a nice program that only does additions, and now I'm paying for all possible instructions I could ever support. It's very costly. So you don't want to follow this approach. This is something I did not realize before because I thought of a CPU as a constant size gadget. Who cares? Care a lot. The way this is handled is, so the approach that we and most others take is to separate the computation trace into different parts. So you're going to have different tables, each table corresponding to one of the operations that the CPU does. So you have an addition table that has all of the additions that happened. You have a multiplication table that has all of the multiplications, and so on, for all of the different tables. And for each one of them, you check it separately. There are not that many tables, so you can do that. You also will need to connect the tables in some way. That's via this memory argument that I kind of skipped over. Okay, so we want to check things differently, check each table separately. How do we check each table separate? The way it's done is you go to each column of each table and encode it separately, or commit to it as a multilinear polynomial. So we commit it to each column separately as a multilinear. Now you only care about additions. You run a zero check to check that all of these additions happen correctly. Does this make sense? Question?
If you wanted to add ZK, I know it's optional. This approach would violate ZK immediately.
And in the sense of the heights of the tables and so on?
Yeah.
So actually, the way we implemented it, padding is for free. So you would possibly not know that your actual heights are smaller.
But you might know if you executed any multiplication instructions or not.
So I want to make sure that the prover doesn't pay for it. But the verifier might be oblivious. So there is still hope. Yeah.
So these
It
are
could be an issue for side channels, but
these are all the additions that happened while you were
and execution.
And execution. Okay.
Yeah, yeah, and multiplication and so on. So there could be like a big time between one and the other, so we have to connect things in some way.
So is this using a jolt-like lookup argument, or is this
No.
separate?
No, this is a traditional before jolt, the separation into different tables was done.
But checking each table, is it done via
The
lookup
way we
arguments?
check each table? No, it's a zero check, sort of like standard zero check
Okay,
protocol.
but like if you have a multiplication, if you have a complicated operation,
Then the constraint polynomial would have the corresponding, would be as complicated as the operation. The thing you can leverage is your constraint polynomial can be somewhat like non-deterministic, so you can add sort of like additional columns that help you in improving the multiplication. So maybe if you're doing additions, on the side you write down the carry bits. These help you a lot, so stuff like that.
So if you want to allow padding for free, then you can only use this discrete log.
No, so we do it with, I can take it offline, we can do it with hashing. Okay, so we separate the trace into tables. We have one per opcode. We encoded each column via PCS. The correctness of each table individually is proved via sum check. When you end the sum check, what you end up is getting a claim about maybe like an entire row in the extension of the table, if that makes sense. And you check that by running your underlying PCS, right? We didn't really write down the entire encoding, but we have access to it via PCS. Okay, does that make sense? So you run your PCS, and I want to focus on this part, checking by invoking the PCS evaluation. So we had our columns, so let's focus on the addition column. We ran our sum check, we got a claim about an extension row, and now we ran our underlying PCS. The PCS is it's a proof of proximity. It will eventually make queries to the actual input. Okay? So these queries are like entire rows that are being queried by the underlying PCS. And you make these queries to get good security, these 100 bits, you will need something like 100 of these rows to be opened.
So in the commitment, you just commit to this. You don't do any kind of extension double in the commitment. You just commit to the computation.
Yeah. So you commit even specifically to columns, column by column, each column separately.
I guess an error correcting encoding.
Yeah. So you commit to, so you do a Reed-Solomon encoding of each column. You do a Merkle tree of that. That's the way the actual PCS is implemented. Yeah. And similarly for all other tables.
What do you mean that you only need to read 100 rows to decommit? I mean, don't you need the commitment? I assume each row in the extension depends on everything.
So okay, so I think I have a problem with the slide. There are two different extensions. One is you actually take the Reed-Solomon encoding of this and extend, but then there are the rows that you care about in zero check are the multilinear extension. So these are taking the actual things that you encoded. So what you do is you take the columns, you encode with Reed-Solomon code, and now you run a proof of proximity on this, and the proof of proximity needs to touch the input. And we call it a constant, but it's security parameter, number of locations. So these are the rows. So far, so good? So the total cost of this opening, if you think of it, is linear in the number of columns times the security parameter. And when I saw this, I had the same reaction that Yael just had, which is like, something is weird here. And the thing that's weird is, we go back to traditional PCPs, the cost of verification is logarithmic. You put your trace and it's logarithmic. And here, all of a sudden, depending on the way you put your trace, you have a linear dependence on the width of this table. And I didn't like that. And it's actually, this cost dominates the verify runtime. So that I found peculiar. And I thought it was a point we can improve. And indeed, that's moving to the third part of the talk, which is the improved version that we have. So what you would like to do, and I think maybe that's maybe what Yael was indicating of do something also this way, we want to encode the entire computation trace as one big happy polynomial. That's what we'd like to do. But on the other hand, we do need, for the zero check, we do need individual commitments to the columns. So let's try to get the best of both worlds. We want to commit to the entire computation trace as one big happy polynomial. We can make the observation that this polynomial, if we put all the tables one next to the other, is very sparse. Right? Because some operations are going to be, you have a lot of additions, not so many multiplication, and so on. So if I just think of a bit like putting all the tables next to each other, it's a very sparse polynomial. And the question is whether you can commit to this polynomial in time that's proportional to its sparsity, rather than the actual data. So this is something that has been studied before. It's called the sparse PCS. It's the same thing as a regular PCS. You want to commit to a polynomial, but you want the cost to be proportional to the sparsity of the polynomial. And we have general solutions. So there's a protocol called Spark by Srinath, and a very recent one called Spark++ by Justin and Srinath. So we could potentially use those, but we're doing this to this 2 to the 30 size computation. We really care about small factor overheads. So we were sort of unhappy. So it's both because it's not fun to use this off-the-shelf solution, and because we realized we can do better. And the reason we can do better is that we have a very particular form of sparsity in our polynomials. Right? The way I like to think of it is that the polynomial we have looks like this. We call it the jagged polynomial because it has these tips. In reality, each one is sort of like an entire table. Right? But think of it, forget about tables, you just have these separate columns, each one of a different height. So that's sort of like how the computation is expressed like. And you can think of it as a polynomial on sort of like 2 sets of variables. So the 0, 1 to the n is indexing the rows, I think you have. So you have 2 to the n rows. That's the maximum number of rows. And you have 2 to the k columns. Okay, so that's sort of what naturally the computation looks like. But I don't want to actually use this because it's very gross kind of and big. So I want to think of like packing all of these columns separately into one like condensed polynomial that looks like this, which has size like 0, 1 to the m, where 2 to the m is the actual data size that you have. Does this picture make sense? And like that, if I tell you like how to go from one to the other, I think it's clear. You squish them all together.
Rotate.
Yeah, you rotate and you squish. First you rotate.
So how should I think of k versus n? The k should be much smaller than n, no?
Yes. Yeah.
K is the distinct operation.
Nice. Yeah.
Yeah. It's not just the number of distinct operations, it's also the width of the individual tables.
Sure.
Yeah.
What did you do here? You started with something that looked like the thing on the right, and then you decided to separate it.
No, so I would say, in terms of the proof system, the sum check and so on, I want to be in this world. In the sense of like committing to stuff, I want to be in this world. And the question is whether I can like be in both worlds and somehow map from one to the other. So that's what we're asking, right? So can I actually commit to this data, but then fake it, like pretend that I actually have this data. So I committed to this data, but now I'm able to prove evaluation claims about this polynomial. Does that make sense?
It's a linear operation.
Indeed. So, okay, so before we get to Ran's comment in a second, the first question is whether it's trivial. And the reason why you might think it's trivial, if I give you 2 multilinears, you can very easily bundle them together. Right? I give you two multilinears, F0 and F1. You can define a new multilinear that has another selection bit, which tells you which of the 2 multilinears to use. So I can just, something you could try to do is take, the 2 shortest columns, bundle them together. Take another one, kind of like a bit like Huffman code. You take the next one, you bundle them together. So you can do that kind of thing. Does this make sense? You run into 2 problems when doing this. One thing is that throughout this process, you keep needing to round to a power of 2, both like the initial ones and then as you go along. And that turns out to be quite costly. Turns out that even worse than that, when you do this kind of thing, because the heights are dynamic, they depend on the actual execution, you don't know them in advance. So you say, so I'll just report them to the verifier. It's not an issue in the sense of like communication, but it does make the way that you bundled your polynomials is not arithmetic in nature. So you could, if the verifier were implemented itself as a RAM program, everything's fine. But in reality, because you want to use recursive composition, you want the verifier to be an arithmetic circuit. So you want things to only be used arithmetically. So you can always emulate the operation via an arithmetic circuit, but there's overhead. So that's why we developed something different, which we call the Jagged PCS. So it's a way to do this form of commitment. And what we show is that there is actually a reduction from claims. You want to prove a claim about p hat, and you can reduce it to a claim about q hat. Right? P hat was the left side, q hat was the right side. The soundness error is good, whatever. Let's skip over the verifier time. First of all, the prover runtime is very fast. So we want to be linear in the number of multiplications. At this point, we're not satisfied by linear. We really want to understand the leading constant. So here it's 5 times 2 to the n plus small order. So at this point, we really want to understand the cost. And communication and verifier runtime are pretty good. Not amazing. Notice that there is still a linear cost in the verifier that depends on the number of columns, which is a thing that feels like fishy. But previously we had like security parameter times 2 to the k. Now it's 2 to the k times m, which is significantly smaller. And I'll talk later about even further improving that. Is the statement clear?
So these are extension field elements?
So where the communication? Yeah, everywhere.
And the soundness error as well.
Yes. Yeah. So how does it work? So Ron's observation is that p hat, so before even Ron's observation, if you look at p hat, the multilinear extension is a linear code. So p hat is a linear combination of the entries of p, right? And I think what Ron was saying is that each point in p corresponds to a point in q. So you can view p hat as a linear combination of q, right?
What is Q?
So P was the sparse thing with the jagged picture.
Q was on the right?
And Q was on the right. Yeah. Okay, so each point, what Ron was saying is that each point in P hat you can express as a linear combination of Q. Not just any old linear combination, it's this linear combination. Well, I just wrote a generic linear combination with these coefficients. What are these coefficients? So it's a function f hat. It depends on the heights of the jagged thingy. But this function f, think of it, so it's a multilinear extension of a basic function f, which gets its input 3 things. So it gets 0 and z column are specifying a point in the sparse picture, and it gets an index I specifying a point in the dense picture, and it's checking are they the same. Is this point in the sparse picture supposed to be mapped to this point in the dense picture based on these heights? Okay? Why is this claim true?
So this f hat has nothing to do with the actual data.
Yes.
It's just the.
It's a mapping. It depends only on the heights.
Yeah.
Yes.
The height depends on the data.
Yes. So only in that way. Yeah.
It depends on all the heights.
On all the heights. Yes. Yes. So I want to prove this claim, and the way to prove these type of claims is by proving the easy version and then extending. So if we assume that all of the inputs, so I, ZR, and ZC, are all live in 0, 1 to the m, then it's clear what's going on here. You're iterating over all indices I. For only one of them would it be consistent with ZRZC, and in that place you'll get the right value. So it's obvious and easy to prove when the case that the inputs are Boolean valued. But we said, 20 minutes ago, that if you have 2 multilinear polynomials, this is one, this is the other, that agree on 0, 1 values, they agree everywhere. Okay? Cool. So we know this. So we know that this holds over all inputs in the extension field. So we're happy. Now we have a claim about this value, and we want to reduce it to a claim about this guy. Any ideas of how to do it? Yeah? Sum check. Okay. So we run sum check. We're happy. We like sum check. It's a very lightweight sum check. And the result of the sum check will be a claim about Q, which we can check directly. That was our goal. And a claim about F hat, right? Do I have like 5 more minutes, or how am I doing? Yeah. Okay. Yeah, very late. Okay, so we want to compute the multilinear extension of this F function. And recall that F was an extension of a function that just checked consistency between the sparse and the dense representations. So first thing we'll do, it's not clear why, rather than sending the heights, I will send the cumulative heights. So we tell you the height of the first column, but then the height of the sum of the first and second columns, and so on. Why, we'll see in a second, but it's useful. It's you can go back and forth, but it's useful. So I'll call it the TJs are the corresponding cumulative heights up to J. And now using T rather than the heights, I want to express this F hat as a simple function. Specifically, I want to write it down as follows. So it's a mouthful, but let's see what's going on with this G. Okay? So what's going on here? Remember, and let's only think for a second about Boolean values, because we're just extending. So I have a point ZRZC, which lives in the sparse representation, and I have a point I that lives in the dense representation, and my goal is to check that they match, right? So here's the idea. I'm going to iterate over all the possible columns. For each column, check. So EQ is checking equality. So I check, am I in the right column? Am I in ZC? If not, I continue. I iterate more. If I'm in the right column, if this guy is equal to 1, then I want to check, So I know I've hit the right column, so I have this call, and I want to check, do I have a match? Right? So I have this G function. What does it need to check? So I want to check that the index I is between the cumulative height up to this column and the next one. And now that I know that I'm in there, I also want to check that it's in the right position. Okay, so you can write down, if you concentrate a little bit, you can write down that G is a very simple, specific function, universal, that just does this computation.
So the equality is also hat, because the Z is not in 0, 1.
Yes, everything is hat. So equality, it's built in with a hat. Oh. It was born with a hat on top.
It's a bit weird that you're not doing binary search.
But I need to express everything arithmetically. So maybe there's a different way, but I don't know. Cool, so remember what we got from this previous sum check was a claim about f hat at a point, and our verifier needs to compute it. What I want my verifier to do is follow this formula. So it can do a sum, so this is the 2 to the k cost. It can compute the EQ guy, but it will also need to compute this G guy at a point, and it's an extension point. It's not just this calculation, it's an extension of that.
Avishai, what he's doing is basically a sum check and the extension. It's a binary search in the extension, actually. Mm-hmm. That's actually what's going on here. So yeah. He is doing a binary search in a sense.
Okay, so to finish the picture, we need for our verifier to be able to compute the multilinear extension of G. Now, we know how to compute multilinear extensions of any function, but it takes a long time. You need to go over the entire guts, which here is enormous. But we have a very simple function. Maybe we can do better. Right? So G is, it was checking that A is equal to B plus C. If you just needed to do the multilinear extension of a function that does that, it's pretty easy. You can write down an explicit polynomial that checks that. The other thing we needed to check is that A is between C and D. You can also do that. But the annoying thing is we need to do both. And in general, if you know that you can evaluate the multilinear extension of one function, and you can evaluate the multilinear extension of another function, it absolutely does not tell you that you can evaluate the multilinear extension of their conjunction. You can evaluate the multi-quadratic extension, but it's not good enough for us. So it's extremely annoying. But it's an annoyance that I'm familiar with. So I've been working on these multilinear-based proof systems for a while now, and we've, in a bunch of papers, we've needed to evaluate multilinear extensions of annoying functions. So this is work with Tom Gore. This is a work not by me, it's by Yael and Tzvika and Justin, and then a work by me and Justin. And sadly enough, we've become pretty proficient in computing multilinear extensions of annoying functions. But actually, it's better than that, because we do have sort of like the theory aspect, and we can only be annoyed to a certain extent in which we try to change things. So in this last work with Justin, we were sufficiently annoyed that we developed a general condition, which is really useful, and I think people are unaware of it. So what we showed in this work with Justin is that suppose that a function G is computable by a particularly weak computational model called the read-once branching program, essentially a streaming algorithm that reads the bits in order. We showed that if this is the case and your memory is this log of W, so the width of the branching program is W, the streaming algorithm has a memory log of W, this is sufficient so that you can evaluate the multilinear extension of G quite efficiently. Okay, time that is, if you think of W as a constant, it's in linear time in the input, rather than naive 2 to the m time that in general it takes. So the corollary out of that if it happens to be that you have two functions, G1 and G2, for which you can compute their multilinear extension because they are from read-once branching program, you can also compute their conjunction, because small space algorithms are closed under conjunction, okay, with an overhead. And given that, I say our own function G, it was conjunction of two things. We don't have time, but it's an easy exercise that each one of them, you can write a small width branching program that computes it. So via this perspective, and I really don't know how else we could have come up with it, because it's really annoying. So I thought to do it on the whiteboard, I won't have time. So just to summarize, what we did is ran a sum check to reduce the claim about p hat to a claim about q hat and f hat. The claim about q hat we check via the PCS evaluation. F hat we compute directly by the means that we just showed. Yeah. This last step is pretty expensive, so we actually delegate. So we need to evaluate G on a lot of points. You can use you can delegate a lot, like reduce many claims about the multilinear extension to one. You can use stuff like the 2-to-1 trick in GKR. There are alternatives that we use. So that reduces the cost for the verifier. And I think I'm out of time, so I'll skip. So we currently, as described, we had the cost that's linear in the number of columns. We have ways to get around it. For the current system, we don't need to. It's cheap enough. So just to summarize, something I tried to convey in the beginning of the talk, there's really massive interest in these type of efficient proof systems, which I think is quite exciting. There's amazing improvement in this space coming from algorithmic improvements. By algorithmic, I mean better proof systems, the kind of things we develop, better engineering and hardware. So GPUs, there are companies looking into developing FPGAs and ASICs to further this. So really exciting. I think the type of theoretical work that we do is interesting in its own right. It doesn't need the practical justification. But if we, in addition, have the practical justification, I think it's great. So I think it's like an amazing success story. So I think that's stemming from the early work in theory from the 90s up to applied work nowadays, and everything that happened in between. 80s even. And the current applications are very focused on blockchains, but because blockchains are so big, this really improves them. And I think once we have these very, very efficient practical proof systems, I believe that other applications will arise. I think verifiable computing as a general paradigm is going to be really important. So I think I'll end here and happy to take questions.
Okay, we'll take one question and then the rest offline so people can head to lunch. But
you said you needed D-log. Where does that show up?
So I hid that. The way that we use the IVC and we check each block separately, actually you want to check that the memory is correct between these. And there are different approaches to doing this. One would be via, like in Yael's papers with Merkle hashing. There's a different approach that we use based on something called the multi-set hash, and it comes into there.
We're returning at 1:30.
Yeah, we're turning 1:30. The rest of questions. Thank you.
I think I would